Morning, everybody. Mr. Stewart here, and welcome to this screencast on linear correlation and determining the line of best fit. So let's get started here. We'll move away from the NG math page and we'll go right into the lesson. So recall that last time we were in class, we were focusing on the equation for the line of best fit. So we left off at this particular page, and this is really the work for today. Okay, so you created a scatter plot on Monday, and today's lesson is going to focus on determining this particular equation here, y equals mx plus b for that straight line. So this should be a review lesson for you, as this is a topic that's come up over grade 9 and grade 10. Okay? So moving forward, what I've done, as you may have already done, is with the example from last class, you're asked to create a scatter plot for the following data. Okay, so the scatter plot is demonstrating what looks like a correlation, and conceivably a strong correlation based on how the points are scattered, of massive corn in grams versus the amount of rainfall in millimeters. Okay. So as for the strength of this particular correlation, that's something that's going to happen in the next class, is we'll also be able to quantify the strength of the correlation. So our next task is to determine algebraically a line, or the equation of a line that would best represent the data. So without technology or other particular methods, we're still estimating. Okay, so there will be some error or some bias, as we've been learning about, in how we place the line and in terms of how we interpret points from the graph. So I went ahead, I graphed a line here that you can see in green, and notice that I did try to make the line go through a number of points, and I was trying to balance out the distance between the points and the line. So for instance, if we were to take into account these distances here above and below the line, really what we're trying to do is to minimize those distances. And in fact, if you take a statistics course in the future for any particular reason, that topic will come up, and the topic of what we call squared deviations from the mean. So that's going to help you in terms of understanding where the equation for the line of best fit comes from. I got a feeling that this particular value here that's in the box may have been a bit of an outlying value, as it doesn't seem to follow the trend. So I tried not to let that sway my perception as to where I would place the line. Okay. Notice also the broken axes that I have here at the bottom. This is going to play a role later on when it comes to determining the y-intercept. So moving forward, what we'll do is we'll select any 2 points that can be read, relatively well on screen. So I could have selected any other 2 points on the line that I felt that I could read accordingly, but I'm choosing these 2. Your 2 could very well be different. What matters is what you end up doing with those points. So if what you do with your points is, if your points are different than what mine are, then maybe pause along the way and just apply what's being said in the video to your own values. So according to my data, I'm going to label the 2 points. So symbolically, I can call them x1, y1, or the first x and the first y, and then x2, y2. So I'm looking at these particular notations here. You can also see that I have that written in terms of its coordinates. So my first one is 83, 78, and then the second one is 115, 108. So those are my coordinates. So notice I'm also dropping in both this horizontal as well as this perpendicular and creating a slope triangle or a rate triangle. So the idea is to determine the rate of change. So if we look to the next step in the process, you'll see a very subtle change So notice that I am now indicating that I'm working with the y values. And what we're doing is determining right here is the change in y, or y2 minus y1. So the difference between the y values. Okay, in like manner, what we can do is also, as you'll see here, determine the difference in the x values, as I'm now working with the 83 and the 115. So we're now determining the change in the x values. So by doing so, what we can do is we can compare those changes. So as far as a notation for the change, okay, so the slope of the line, so notice I've labeled the slope as m, and it's a ratio. So you remember rise to run, which is the difference in the y values compared to the difference in the x values. And then b is the y-intercept, and xy is any point on the line. Okay, so now that we have a relationship and we know what the difference is between the y values and the x values, we can find a rate of change. So that rate is 30 seconds, or 30 over 32, and in lowest form, 15/16, or 0.9375. So what's just as important as calculating that is determining the significance of that. Okay, so because y is the growth, okay, so along the vertical axis, I believe that was the growth of the corn in millimeters or in grams. I guess it was production, so corn mass in grams. Whereas down here along the horizontal, that was rainfall in terms of millimeters. So what that means is that as far as rain is concerned, so for every 16 millimeters of rainfall, we can anticipate on average, according to the line of best fit, that we'll have 15 grams of production. Okay, so that's the significance of the slope. So therefore, our equation so far is y equals 15/16, or 0.9375 times x plus the yet unknown y-intercept. Okay, so we need to have a y-intercept because, as you can see, the line most likely is not traveling through zero. So it's not a direct variation. So the growth of the corn doesn't directly depend on the rate of change that we have. There will be some adjustment factor, okay, over this y-intercept. So let's move forward to see what happens. So again, feel free, do pause if and when you need to, or rewind. Certainly if you're watching on your own, and take some good notes to capture your thinking. And as you're thinking on the video, do make sure you write down and capture that. So because x, y is any point on the line, we can go along. We can choose maybe one of the points we already have, or maybe we can choose another point. I like to choose a different point in case I've introduced maybe some form of error using the original point. So it's always good to try something different. So I've chosen this particular point. You might choose something else. So I'm using 103, 96. So what I'll do is I'll substitute those values in. So you can kind of see by color code where those particular values are going. Now, next up, what we'll want to do is we'll want to clear the denominator. So meaning we're going to clear that 16, or division by 16. So if I want to clear division by 16, or find its inverse, doing the inverse means to multiply by it. So notice that every term gets multiplied by 16. And then 16 cancels, or meaning that we're left with 1 over 1. Right? As 16 divides into itself one time. So the equation cleans up as the following. So I've done the multiplication, and I've actually started isolating the value for b by moving the 1545 to the left-hand side. To last but not least, let's divide both sides by 16. as you can see being done here in this particular line of the solution. And we end up with a y-intercept, which is just less than 0. So negative 9/16, or as I should be writing here, negative 0.5625. Okay. So therefore the equation is as follows. Y equals 15/16 x minus 9/16. Or given that the decimals are relatively clean, they terminate with the 5. So 0.9375 and 0.5625. That's also a reasonable set of values to use if you're calculating by hand. Okay, so all in all, this equation describes that line, and we can use that line to predict the growth in corn relative to the amount of rainfall received. Now, that 9/16, again, negative 9/16, that's fairly small. You might be wondering why, given the graph as it is, why it's not more. Like, why is it not, 50 something? Right? Should it not be here if we extend the line? The answer to that is flat out no. Okay, because if you look at how the scale, right, we have a broken axis, so we are missing a lot of values there. So if we were to expand this out, that line should drop down to a position that's roughly close to 0, or at minus 0.5. So now that we have the equation, what good is it? Well, as you know from other work in our course and previous courses, there's a lot of predicting value within that. And let's see, I'm skipping ahead here a little bit. Okay, so part C says to pose and solve a problem where you can use your equation to interpolate some other value. Now, to interpolate means to look within the data. So for a line of best fit, that's okay most of the time. So what we'll end up doing to do the interpolation, so let's say for 100 millimeters of rainfall, if you go ahead and calculate that with your equation, I would actually have you do that. Substitute x and do some operations to calculate y. So you should get about 94 grams of corn. Now, for the second question, I'm just going to close down this information bubble. For the second one, I've made up a question here. That is, if the trend continues, what amount of rainfall would produce 120 grams of corn? Now, it's okay to use the line for that, but again, much like we learned about other filters through which we run our decisions, right? Critical thinking is important. So we're looking at outliers, we're looking at the strength of the correlation, we're looking if bias has been introduced even in the early stages of collecting data, well before representing on a graph and calculating the equation. Is in the next lesson, you'll catch a glimpse of something called the coefficient of determination. And that coefficient is going to be helpful in determining whether or not we should move forward with the extrapolation. And the extrapolation means looking beyond the graph, okay, or beyond the data that we have. So for this one, it's actually the inverse. So in terms of solving for the rainfall, we have to substitute 120 for the y value, and we'll solve for x. So I would encourage you to try that too for yourselves. So as you go through the process, take a look at your equation solving process, which I'm identifying here is you're going to have to balance the equation out by removing the y-intercept from both sides. And computer seems to be lagging a bit here. And then dividing by 0.9375, which is your slope. So to wrap things up, again, pause, rewind, rewatch, make sure that you get some good notes in. And if you have any questions, do jot them down and bring them to my attention. The follow-up for this is the following. You have a few questions to consolidate your learning. Note that I was not able to produce in time the enlarged graph for number 7. That's something that you'll have to do for yourselves. Okay?